Hello friends and welcome to this video. We are with the last chapter of Advanced Digital Signal Processing subject and the chapter is titled Applications of Signal Processing. Various signal processing methodologies those we have covered in the previous chapters. The associated popular applications we are discussing in this particular chapter. So the applications include signal detection, spectral analysis of sinusoidal signals, speech signals, random signals, the music sound processing we have seen, digital music synthesis also is referred to, analytic signal generation, signal compression. In the previous two videos, after transmultiplexes, we have seen multi-tone transmission of digital data also. So in this list, let us add one more, that it is oversampling A to D converter. So to see the details, let us begin with this topic. So here we can start with our topic, the topic titled Oversampling A to D converter. So as far as the digital processing for analog continuous time signal is concerned, we know that to make it into the digital domain, the signal which is basically in analog or what we can say continuous time signal domain is first of all to be passed through the sample and hold circuit, and the output of this sample and hold circuit is further converted into digital form by the help of A to D converter. Now, according to the sampling theorem, there it is a requirement that the band limited continuous time signal with a low pass spectrum can be fully recovered from its uniformly sampled version if it is sampled at a sampling frequency that is at least twice the highest frequency contained in the analog signal. This is the very important theorem in the communication of the data, so that it is sampling theorem, and the condition of the sampling frequency to be at least twice the higher frequency should be always followed, otherwise we will be having loss of the information. See, if this condition is not at all satisfied while designing the communication system for the digital data, the original continuous time signal cannot be recovered back at the receiver end, and that is by using its sampled version because of the aliasing effect. Now, we don't want any aliasing to occur practically, and therefore the analog signal is first of all passed through an analog anti-aliasing low pass filter, which is the section prior to the sampling process that also enforces the condition of the sampling theorem. Now the passband cutoff frequency of the low pass filter is selected as such to be equal to the frequency of the highest signal frequency component that needs to be preserved at the output. The anti-aliasing filter also cuts off all the out of bound signal components and any high frequency noise that may be present in this original analog signal, which otherwise would alias into the baseband after sampling, and the filtered signal is further sampled at a rate that is at least twice that of the cutoff frequency. So in this regard, let us assume that the signal band of interest will be of the frequency range small f, that is greater than or equal to 0 but less than that of the capital F suffix m. So therefore the Nyquist rate can be given by the relation capital F suffix capital N to denote the Nyquist, that is equal to twice of capital F suffix m. Now to look at this relation, if we have the sampling rate denoted by capital F suffix capital T in general, which is equal to that of the Nyquist rate, so that time we require to use the sampler and anti-aliasing low pass filter with very sharp cutoff in its frequency response, satisfying the requirements as discussed here. Now this particularly requires the design of a very high order anti-aliasing filter structure built with the high precision analog components and it is usually difficult to implement such a filter in generally, for example, the VLSI technology. So practically using such type of filter, there it is a chance of distortion into the output signal. So therefore we have an alternative approach to cope up with this particular condition, and the alternative way is to sample the original analog signal, that is the continuous time domain signal, at such a rate which is much higher than that of the Nyquist rate. That is why our today's topic of discussion is oversampling, as we are keeping the sampling rate very much higher than that of the requirement of the Nyquist rate. We say here it is oversampling here, and thereupon we will be using the fast low resolution A to D converter and further decimating the digital output of the converter to the Nyquist rate. Now this approach of oversampling A to D converter is very beneficial in many aspects. So in this concern, let us illustrate the noise performance improvement property for this A to D converter that is operating at the sampling rate in general capital F suffix capital T in terms of hertz here. So now for the full scale peak to peak input analog voltage, the smallest voltage step can be represented by B bits here, and here this particular step can be denoted by delta V, that is equal to capital R suffix Fs, which is the peak to peak analog voltage, which is divided by 2 to the power B minus 1. So B, as we have represented, B is the number of bits here, and the equivalent representation for this step can be equal to the ratio capital R suffix Fs divided by 2 to the power B here. Now the RMS quantization noise power, that can be denoted by sigma suffix E. Sigma is squared, that is the variance of the error voltage, with the assumption that uniform distribution of the error is there between minus delta V by 2 plus delta V by 2, which can be expressed as sigma suffix E. Sigma is squared, we express it as square of delta V divided by 12 here. Now the RMS noise voltage, that can be given by the deviation sigma suffix E, thus has a flat spectrum into the frequency range from 0 to ft by 2. The noise power per unit bandwidth will be called as the noise density, expressed by the expression capital P suffix E comma n, that is equal to square of delta V divided by 12. This is completely further divided by ft by 2. So the simplification leads to the right hand side equal to square of delta V divided by 6 times ft, the sampling rate here. The corresponding graph of the noise densities for the two different sampling rates can be illustrated with the help of one schematic here. So in this illustration we can see the node density, noise density versus the frequency here. So here we are having the low sampling rate and the high sampling rate here. From this illustration, whatever the shaded portion you see, that is basically the signal band of interest. And from this illustration, we come to see that the total amount of noise in the single band of interest for the high sampling rate is smaller than that of the low sampling rate if it is the case. The total noise in the single band of interest will be called as in band noise power, and it can be expressed by the mathematical expression. We denote it as capital P suffix total, expressed in terms of square of R suffix Fs divided by 2 to the power B bits. This is whole divided by 12, and this ratio is further multiplied to another ratio where numerator is F suffix m and the denominator is Ft by 2 here. Now for computing the needed word length, that generally we can denote by beta for the A to D converter operating at the Nyquist rate, for the total noise in the single band of interest to be equal to that of the B bit A to D converter operating at a higher rate here. So let us have the substitution. Sampling rate Ft is equal to twice of Fm as per the Nyquist criteria, and let us replace small b representing the bits by the word length beta here. So the new equation for P suffix total will be equal to RFS divided by 2 to the power beta, the ratio is squared, which is further divided by 12, that is equal to RFS by 2 to the power b squared divided by 12 multiplied to Fm by Ft by 2, the previous representation. So for this modified expression, we have the relation of beta with small b. Beta is equal to small b added by 1 by 2 times log to the base 2 of capital M, where capital M is the oversampling ratio that we can abbreviate to as capital OSR. So for improvement into the noise performance, here it is the structure that is of oversampling sigma delta A to D converter structure. So here we have analog input at the left hand side fed as input to the summation, where we have the further blocks of analog integrator, 1 bit A to D converter and a feedback loop by 1 bit D to A converter. So this much of portion is the sigma delta quantization process, and next to that we have mth band digital low pass filter and then the decimeter here. So the complete decimeter we can say with the filter structure and the decimation factor denoted by capital M here, finally resulting into the digital output here. Let us have a look on to the example for the compact disc that is having encoding system for one channel of the stereo audio here. So for example, we have the analog audio signal fed as input. Here we have the blocks A to D converter, further parity coding, multiplexer which is having one input from control and display coding. Next to that, very important modulation process is to be done, and again we have multiplexer and a signal from synchronous pattern generator, finally resulting into the digital bit stream here. Now for better understanding of the oversampling sigma delta A to D converter structure that we have shown previously, we need to also have a focus on sigma delta quantization scheme in terms of the quantizer circuit as given here. Here we have the integrator, A to D converter and D to A converter, and next to that corresponding discrete time equivalent circuitry is also represented with the delays as denoted z to the power minus 1. We have the use of accumulator, the quantizer, the signal representations at the various stages. As for the input case we have x of n, for the output we have y of n, the intermediate stages after the accumulator w of n, and for the quantizer the error is denoted by e of n. So for this oversampling sigma delta A to D converter structure, we are going to also have the implementation of sigma delta quantization scheme into the MATLAB environment into one of our next videos after completing the theoretical discussion on all these applications, so that it will be at the end of the chapter here. The corresponding input and output of the sigma delta modulator, here we have the typical illustrations. So this is the input analog signal fade, so that is amplitude level less than 1 here. So the typical value, let us say we have 0.8 here, and here we have the time axis from 0 to 20 samples here. The corresponding output of the sigma delta modulator is illustrated here with again the amplitude versus the time here. So all the discrete samples are represented here. So this becomes the case of constant amplitude signal fed as input for sigma delta quantization. On other hand, if we have the sigma delta quantization done for the input signal to be of sinusoidal type here, so this is what the corresponding input, and further we illustrate the output also, the typical input of sinusoidal type. Here you see, so the amplitude level maximum is less than that of the 1 here, and it is having the repeating sinusoidal nature here. So the time samples are 0 to 100 here, the amplitude markings are there on vertical axis here, and here it is the corresponding output here. Now next to that, we have the input and output waveform for the sigma delta quantizer, and further the low pass filtered version of the output signal illustrated with this particular diagram here. Now let us continue the discussion with respect to the equivalent structure of sigma delta structure that we have seen before, where the output is denoted by y of n. So this output y of n will be the addition of w of n with e of n, and here the w of n is computed as x of n minus y of n minus 1 added by w of n minus 1. Now from these two equations having certain manipulation, we express y of n is equal to x of n added by in the bracket e of n minus e of n minus 1 here. Here the quantity inside the parenthesis that we have denoted e of n minus e of n minus 1 is representing the noise level due to the sigma delta modulation process. The noise transfer function can simply be denoted by capital G of Z, and the power spectral density of the modulation noise can be denoted by capital P suffix y of f, that is expressed as mod square of capital G of e to the power j times 2 pi ft multiplied to P suffix e of f, which is further expressed to as 4 times sine square 2 pi ft divided by 2 into P suffix e of f. So here the assumption is that the power spectral density that we have P suffix e of omega for the quantization noise to be one-sided power spectral density defined for the positive frequencies only. Now for the random signal input, as generally we have been denoting by x of n here, P of f is constant for all the frequencies, and that is expressed as square of delta V divided by 12. Further, this is all divided by ft divided by 2. Now if we can have substitution to the previous equation of Py of f, we get the simplified representation. Py of f is equal to 2 by 3 times the square of delta V divided by ft, that is further multiplied to sine square pi ft. Now for very large OSR value, the frequencies in the signal band of interest are much smaller than the sampling rate ft. So the sampling frequency that it is, we approximate for P suffix pi of f is equal to, we have 2 by 3 multiplied to the square of delta V divided by the sampling rate or sampling frequency you call ft. This is in multiplication to the square of pi ft here. So at last we write it to as 2 by 3 times pi square multiplied to square of delta V into cube of capital T into f square, where f is very smaller than the sampling rate ft here. Now from this particular equation, the in-band noise power of the sigma delta A to D converter can be expressed as, we write here, P suffix total comma SD, that is equal to the integral 0 to f suffix m for capital P suffix y of f into df. So this is equal to 2 divided by 3, which is further multiplied to pi square of delta V t cube integral 0 to fm for f square df. This is equal to 2 by 9 pi square of delta V multiplied by t cube into fm cube here. Now if the noise performance of the sigma delta A to D converter for the direct oversampling A to D converter operating at the sampling frequency of ft with the signal band of interest from DC to FM, if compared, the in-band noise power is given by, for the second case, P suffix total comma OS, that is expressed as 1 by 6 times square of delta V into capital T into FM. Now the improvement into the noise performance is expressed as 10 log to the base 10 of P total OS divided by P total SD. This is equal to, we substitute, so 10 log to the base 10, 3 capital M square divided by pi square, So this is also expressed to the form minus 5.1718 added by 20 times log to the base 10 of capital M in terms of decibels, where capital M is equal to Ft by twice Fm for denoting the OSR. So for example, OSR, if it is computed for M is equal to 1000, the improvement in the noise performance using this particular scheme is about 55 decibels here. So the increase in the resolution here we find that is 1.5 bits per doubling that of the OSR. So this way we have seen the oversampling A to D converter approach for avoiding the undesirable phase distortions in the design of anti-aliasing filter structure. So after completion of this topic, oversampling of A to D converter, by the next lecture we shall address another topic of oversampling. So this time it will be oversampling D to A converter from the same chapter, applications of signal processing. Thank you.